Alright, welcome back folks. Our mission today is to take the hypothesis testing framework in that ANOVA test that we discussed in the last video and look at how it would work with real data. We've got our new friend, the ANOVA table back here. We're going to use this in step 4 to fill in some of the key information that leads us to get to that F ratio that we really want. But first we are going to start by progressing through the initial steps. So here's our premise. Let's say that we are interested in looking at people's scores on an anxiety test. Now, an anxiety test can be used for a number of things, but one of them is to diagnose people, whether or not they seem to have a clinically high level of anxiety or not. So to validate a measure like that, you need to make sure it can tell the difference between people you already know have anxiety disorders and people that you know do not. So let's say that we take 4 samples of participants and each one is representing its respective population. We have people with no specific anxiety disorder at all, and then we have 3 different types of anxiety disorders: panic disorder, generalized anxiety disorder, and social phobia. We see some basic information here. We know the number of people in each group. It's not exactly even. That's oftentimes true in research. We see the sample means there, and we can see that our anxiety groups do score higher overall, but is it significantly higher or not? Is it large enough to make some conclusions about the population? So we're going to use an alpha of 0.05 as we generally do, and we're going to see if these population means appear to significantly differ. All right. We start things off by describing our hypotheses, and again, it can help to first discuss the populations that you're comparing. There are 4 of them. Population 1 is represented by those 4 folks in the sample, our non-patients. Population 2 is our panic disorder folks. Population 3, our generalized anxiety disorder, and 4, the social phobia. So these are the populations our hypotheses are going to revolve around. The null hypothesis is simply that they all are equal to one another in terms of their average level of anxiety. You could say mu1 equals mu2 equals mu3 equals mu4. It's a little bit of a mouthful. It doesn't take too long to write out. Or you can just write it out in English this way. The 4 populations have equal means, or the same level of anxiety. The alternative, you do not want to try and write out symbolically because there are lots and lots of different ways the null could be false. So we lump those all together to just very generically say at least one of the 4 populations has a different level of anxiety. Maybe more than one, maybe all of them, but at least one. Notice again, if we reject the null, we are not going to know which populations differ or how many of them significantly differ. Put a pin in that, keep that in the back of your mind. We're going to have to figure out a way to resolve that eventually, but for now, we're just going to see if we can reject the null or not. Step 2, remember step 2 gets real fast in the ANOVA. You simply define the shape of the distribution. That involves calling it an F distribution and calculating the between and within degrees of freedom, sometimes called numerator and denominator degrees of freedom. So how did I get 3 and 8? Well, degrees of freedom between is the number of groups minus 1. There are 4 groups, so your degrees of freedom between is 3. Within degrees of freedom, I could subtract the number of groups from the total number of participants, but instead I'm going to do n minus 1 for each group separately and add them all up. 4 people in the first group, 4 minus 1, that's the degrees of freedom for that group. Again, do it for the other 3 groups, add them up, a total within degrees of freedom of 8. Notice if you add these 2 numbers up, they add to 11. That's the n minus 1 for the entire distribution. There are 12 people, so these should add to 11. A good way of checking your work at this stage. But real quick step, just involves does really quick calculations of those degrees of freedom. Then we have to determine the critical value or the threshold value. Again, that involves using our alpha, our 2 different degrees of freedom. And in this class, you'd be using the F table. So if we use the F table to look up those critical scores, what we would find, and you can do it yourself, is 4.07. What that means is that F ratios that are larger than 4.07 have a smaller likelihood than alpha of happening if the null was correct. So that's steps 1 through 3. Those should go really fast once you have a couple repetitions under your belt. Again, step 4 will take longer than the rest of them put together because this is where basically all the calculations happen. So we've got our ANOVA table here, and for space's sake, I didn't write the critical value under it, but you might want to do that as well. It's optional. Again, this whole table is optional. You don't have to make it. I'm not going to check you making it, but it makes it easier to organize information and harder to make the kind of silly mistakes that you really want to avoid. So we always enter step 4 with some of the information on this table. We know the degrees of freedom. We got them in step 2, so we can fill those in. And to get the total, all I did was add them together. So nothing too tricky there. The first step, again, to filling in the blanks is to calculate those sums of squares. And again, make sure you're very comfortable with that sum of square formula. It's going to come up. It's going to be on the exams. If you're good at it, those are basically free points. If you're still struggling with it when exam day rolls around, it's going to potentially seriously impair your ability to get a good grade. So make sure that you keep working on sum of squares until you are comfortable knowing which numbers you're plugging in and how to calculate it. So again, some of the relevant sums of squares formula, there's so many of them, but they boil down to doing the same thing multiple times. This is the sum of squares formula for sum of squares total, and the total just means that we're going to include every single score in the entire data set. Again, notice this is the numerator for our computational variance formula. It's not a coincidence. You can use the definitional formula. I'm not going to show it to you. We're not going to work on it. It takes a while to do, but if you can get the right answer that way, I have no problem with it. For sum of squares within, we're going to use that same formula, but just for each group separately. Then we're going to add them all up. And then fortunately, the sum of squares between, you just subtract within from total. Whatever's left over, that's your sum of squares between. So notice that we've seen averages and we've seen ends. We haven't seen any individual scores yet. We're going to get to that in a moment. Once we have those sums of squares, we're going to just divide across our board here, numerator, denominator. There's your mean square between. Numerator, denominator, there's your mean square within. Again, mean square is just another way of saying the variance between and within groups. And then the F ratio right here, you've already got your numerator and your denominator all lined up. So let's look at our actual data. So here's our real data sets, and I've filled in some of this basic information down here. Again, I'm going to mostly skip these basic steps that we've done before, but I encourage you to work on them on your own or to revisit the old module videos if you're having trouble with them. But here are 4 groups, and here we see individual scores for each group, and then squared scores for each group. Why did I choose to square them? Because I'm going to need that for my sum of squares formula. On a test or paper, you'd really just have this first column here. Notice at the bottom of each group, I've done a sigma x and a sigma x squared for each group. I'm going to need those for my sum of squares within formulas. I can also add them all up and get my sigma x total. Sigma x total is just every single score in the data set all added up. It doesn't matter what group they're in. Sigma x squared total, every squared individual score added up across all conditions. And the only other thing we would need is the n, which is 12. By the way, you should check and make sure your sigma x's for each group add up to your sigma x total. Same thing for your sigma x squared. But at this point, we have all the numbers on the screen that we are going to need to calculate all of those sums of squares, the mean square, and the F ratio. So let's jump in. Sum of squares total involves taking these total figures here, all the scores squared and then added up, 1269. Then we take all of the scores added up, 121. We square that, we divide it by the number of people in the group, and then we subtract that from 1269. We wind up with a sum of squares total of 48.92. 48.92 is what that's supposed to read. Hopefully my penmanship is sufficient. Then we have to calculate sum of squares within groups. The way that we do that again is we use that same sum of squares formula. We do it first just for our non-patients, then just for our panic disorder, just for GAD, just for social phobia, then we add them all up. So this looks a little intimidating, but just one piece at a time. This is that same formula done just for group 1. Notice the sigma x squared and the sigma x have migrated down there. Also notice we use the n for each group. It's 4 in this group. For the second group, panic disorder folks, it's only 3. Make sure to keep that straight. Here's the sigma x squared and sigma x from that group, and then so on and so forth. You can see each group, their information is getting pulled into their formula. Again, by the magic of made-up numbers, every single one of them translates to a round number. Real data is not usually so friendly. I do want to point one thing out for you. Our third group has sum of squares of 0. How did that happen? Take a look at this. See if you can figure it out. Why would that produce a sum of squares of 0? And the answer should be because the variability is 0. Both of the scores are exactly the same. They're not varying, so the sum of squares is 0. Either way, when we add all 4 of those individual sums of squares up, we get 18. That is our sum of squares within. There's 18. Then the sum of squares between, hey, we just subtract whatever's left over. After those first two sums of squares, the total and the within, it starts moving really fast. It's just some subtraction and division. You just got to make sure you do it right. So we subtract within from total, and our sum of squares between 30.92. All right, just a couple more steps to go. You're actually almost there. We divide across, sum of squares between divided by degrees of freedom between. After rounding, we get a mean square between of 10.31. Do the same thing for our mean square within row here, 2.25. Sometimes people ask, why don't we do the same thing for the total? Well, the answer is, gosh, you can if you want to, but I'm never going to ask you for it, and it doesn't play a meaningful role. So let's just skip it. But you could divide across if you wanted to. But notice again here, we have the numerator and denominator of our half ratio nicely lined up. We divide 10.31 by 2.25, and we get 4.58. What this is literally saying is there's 4.5, a little over 4.5 times as much between groups as within groups variance in our data set. All right, so that's our test statistic, just like the Z and T scores we've used before. We compare it to the critical value, which is 4.07, and do we reject the null? Yes, we do. 4.58 is over the line. It is within the region of rejection. Its probability is lower than alpha. So we reject the null and conclude that at least one of our populations is different from the rest. Which ones? We don't know. How many? We don't know. But we do know that we can reject the null and say there's some kind of a difference at a population level, meaning this anxiety test does appear to produce different average scores across those different populations. We'll figure out how to add clarity next video using the same data set. So we will talk about these post-hoc or follow-up tests, but for now, just make sure you're familiar with the basic process of hypothesis testing in ANOVA. See you in the next video.